Okay, so I'm probably going to have to do this video in a couple of parts because I have another class, but this is going to be part one of the video tutorial for the review. There may be a part two. We're going to see how it goes. And I'm going to just take it from the top. This is very basic. This one's asking you to identify reactants and products. This is going to be for every single balancing. It doesn't matter if you're dealing with a combustion or a synthesis, decomposition, any kind of reaction, the reactants are always going to be here. The products are always going to be on the right side of the arrow. Always, always, always. Doesn't matter. So if it's asking you to identify the reactants, it's just going to be what's to the left of the arrow. There they are. Okay, a balanced chemical equation is a direct representation of the law of conservation of mass. That's just what it is. In order to balance a chemical equation, one must use coefficients. Coefficients are just the big number, like for example, in these below, that's a coefficient. Okay. So this one actually has a little typo because it says number 1 and that has calcium, but the idea is still the same even though this one's showing copper. We want to find the correct balanced chemical equation. So there's no really way to do this except for looking at each choice. This one I have 2 coppers on the left side, but on the right I have, let's see, on the right I have 2, but my bromines aren't right, because on the left I have 1 and on the right I have 4. So choice B, let's see, on this one I can see that my hydrogens are not the same. On the left I have 2, on the right I have 4, so that one's out. And on the next one I can take a look. I have 1 copper on the left, 1 on the right. I have 2 hydrogens on the left, 2 on the right, and 2 bromines on the left and the right, so this one's balanced. And I'm just going to look at D just to be sure. Let's see. And here my bromines are wrong. So, it's going to be that one. Okay, so this is probably where those were pretty simple, and we're going to look at the next ones. So, first we're going to balance, and then we're going to write the reaction type. Alright, so here I have 2 hydrogens on the left. Remember, you can always just turn the arrow into an equal sign, and from there we're just counting. Okay, so if I have 2 on the left, that means I also need 2 on the right. I can't change subscripts, but I can change coefficients. Now I've also affected the number of bromines, because the coefficients go to everything. So now I have 2 bromines, but that's okay because I have 2 on the other side. So now this is balanced, and I'm just going to finish it off by writing the 1s in there, because we need to write the coefficient of 1. Alright, now we want to look at the reaction type. I have seen some confusion with this. You just need to look at what is on each side and kind of figure out what's happening. So we have some hydrogen on the left side and we have some bromine, but they are not together. So what happened is they came in, the reaction occurred. This is a synthesis reaction because we had 2 separate products. They came together and formed a single compound. That is synthesis. Alright. Now I'm going to balance this one. Okay. So I'm going to start with the fluorines because these are the least balanced for every kind of reaction aside from combustion. It doesn't matter which one you start with. Okay, so with the fluorines on the left I only have 1, but on the right I have 4. So I'm going to go ahead and put a 4 over here. That has changed my hydrogens as well. Okay, so my fluorines are balanced. I have 4 and 4 on each side, but my hydrogens are now not balanced. I have 4 hydrogens on the left, but I only have 2 on the right. I'm going to fix this with a coefficient of 2. Because 2 times 2 is 4. But I also changed my oxygens. Now I have 2 oxygens. That's okay because on this side I already had 2. And I have 1 silicon on each side. So now it's balanced. and I want to look at the type of reaction that occurred. Okay, so I have two different compounds on each side, and what happened was that they just switched partners. So this is a double replacement reaction. I think sometimes it's easier if you kind of highlight it a little bit to see what's going on. Okay, so I'm just highlighting to represent my cation-anion situation, or your metal-nonmetal. Remember, hydrogen acts like a metal in a lot of ways. But all they did was switch partners. So silicon was paired with oxygen, but in this double replacement reaction, what ends up happening is they just switch partners. See how the fluorine was paired with hydrogen, but then they just switch. So now the silicon is paired with the fluorine, and the oxygen went over there with the hydrogen and made water. Okay, so that is the double replacement reaction. These look different from all the other reaction types because you're starting with two compounds and you're ending with two compounds. Nothing is alone, and that is why it is a double replacement reaction, not a single replacement reaction. And I'm going to mix it up a little on this one. So here's the deal with water. If you ever see that one of the sides has OH as a product or a reactant, it is best to turn that water into something that resembles an HOH. That's because it will allow you to more easily see what's going on. HOH is the same thing as H2O. It just makes it easier when you're balancing. So I'm going to just cross that off and write HOH, because that way I'm just more able to easily see that this is a single replacement reaction. So basically the potassium came in, kicked out the hydrogen, took over where the hydrogen was. So now it's KOH instead of HOH. But this is very hard to visualize if you don't change this over to HOH. It's also very hard to balance. Okay, so this is a single replacement reaction. I can treat my OH as a group. So I can say on each side I have one OH. So we'll keep on balancing. My H2s are not balanced because I have two on this side, but I only have one on this side. Because again, we separate the H's from the OH's. They're acting as an independent hydroxide unit. So I'm going to fix this. Now I have two hydrogens, but I also now have two OH's. Again, easy to fix because we can treat it as a group. Alright, so there's my potassium. I've also affected the number of potassiums when I balanced my hydroxides. So I'm going to balance that. And now I'm all balanced. So that's a single replacement reaction. So my number one tip is if you ever see an OH on your product or reactant side, I would change the water. And this one, that didn't happen because I didn't have an OH, so I didn't have that consideration. But if you see an OH, change the H2O. It makes it simpler to balance. Alright, this is another single replacement reaction. I can tell that without really even looking in depth too much because I have a single and then I have a compound, and then on the product side I also have a compound and one all alone. So once again, just like before, hydrogen got kicked out, just like in the one above. And that is because if you look on the activity series, magnesium is going to be higher. So here's my activity series. This question isn't asking this, but just to tie that all in, hydrogen's down here. So if magnesium came in there and was trying to replace it, that's a good replacement. It's higher on the list. It's a better deal. So that's why it got replaced. And now I just have to balance. Anytime you have a polyatomic ion, go ahead and put a parentheses around it if you want to. It might make it easier for you to remember that we treat these as a group. Our buddies stick together. Don't break your buddies apart. So I don't want to have anyone sitting there trying to separately balance the S's and the O4s because you don't have to do that. I'm just looking at this right off the bat. It looks like I have one SO4 on each side. Alright, so let's see. We've got one magnesium on each side. We've got one SO4 on each side, and we have 2 hydrogens on each side, so this one's actually already balanced. That's easy. That happens sometimes. Alright, what's going on in this next one? This is a double replacement reaction, and I can tell that right away because I have a compound, and then they switch places. Okay, so the lead was with the NO3, but then the lead instead ends up switching and gets the second one here, while the sodium gets the NO3. So all they do is switch partners. So you take, if you wanted, another way to think about this is if you label each part like A, B, C, D. So originally C and D were paired together, but look what happens. The C now gets with the B, and the A gets with the D. So that's another way you can look at it, if that helps, if you don't like colors as much. Alright, I have 2 NO3s on this side, but I only have 1 on this side, so I'm going to balance that. Okay. That also affected my sodiums, so I'm going to go back and balance those. And let's see what we did with my iodines. There's already 2 on that side. There's 1 lead over here. We've got our NO3s balanced. I think we're good to go now. And again, that's a double replacement reaction. Okay, so I'll come back and do part 2 in a little bit. Okay, so here's some more of this review. I'm going to pick up with some of the, just talk you through some of these reactions and what we did here. This problem number 10, this is a combustion reaction. I know it's a combustion reaction because I only have the C, H, and O. So if you only see C, H, and O, and especially like if you're looking, that's all that's on either side of products and reactants, especially if you see the carbon dioxide and water, because these are all set up the same way. So they'll all have the C and H in some combination, then an O2 next, then a carbon dioxide, and then a water as their products. So how do we want to solve these? The first thing you're going to do is always put a 2 in front of the hydrocarbon. That's the combination of the carbons and hydrogens. Always start by putting a 2 there. That will fix any problems you have with not having the correct numbers of oxygens at the end. So if you start by putting a 2 there, it will save you some trouble later. Then you want to make sure you solve them in CHO order. In other types of balancing, any other reaction besides combustion, you can kind of start where you want to, but in these it is easiest if you solve by balancing the carbons first. So that's what we're going to do here. On the left side you have, once you have your coefficient in there, you're going to say 2 times 5, that is 10. So in order to balance that, I put my 10 coefficient on the right side. Now I have 20 carbons on each side. I'm sorry, 10 carbons on each side. Getting one step ahead of myself. So I have 10 on the left, 10 on the right. Okay, my carbons are balanced, and now I'm going to move on to my hydrogens. On the left side, because I have that coefficient of 2 down, I'm going to say, alright, 2 times 10 is 20. So on the left side, I have 20 hydrogens. On the right side, in order to make it also 20, I need a coefficient of 10, because 10 times 2 is 20. Okay, so I have 20 carbons, 20 hydrogens and 10 carbons on each side. The very last thing you're going to want to balance are your oxygens. So before I put my coefficient there, I had 2 oxygens on the left side, but if I move over to the right, you have to remember that an oxygen is in 2 different places. So I have oxygen in the carbon dioxide and also in the water. So I want to count up and make sure. So my coefficient from before, when I balance my carbons and hydrogens, applies to the oxygen, because remember, coefficients carry over. So I have 10 times 2, that's 20, plus another 10 from the water to get a total of 30. So I have 30 on this side, and that's where that 15 came from, because I also need 30 on the left side. Very important to balance that way. Alright, so how do you know what kind of reaction you're dealing with? This is just going to take a little bit of practice and some reading. So I knew this one was a double replacement reaction. Okay, this is a double replacement reaction because I'm just reading. The first one is a compound, and so is the second one. That means I'm looking with a double replacement reaction. There is a sum. I just got that by writing things out. Don't panic, just write it out. So I'm just going to write out AgNO3. The 2 came from the NO3 because that has an oxidation number of 2. And when I'm writing my acid names, again, don't panic. You know how to do this. It says hydrosulfuric acid, so that's acids all start with H. That's where the H came from. The hydro is telling me it's binary. That's acid naming. The 2 came from the sulfur. Because this is a double replacement reaction, when I'm writing out my product side, and this is the side where I've seen some nervousness, but don't panic. Just look at the pattern. Okay, the silver is going to get with the non-metal, because silver is a metal, from the other side. All they're doing is changing partners. So if you look, the silver was originally with the nitrate. All they do is switch partners. So now the hydrogen is now paired up with the nitrate. Hydrogen acts like a metal in this case, and it gets the non-metal from the other side. So that's all we did here. They're just changing partners, like I showed you before with that A, B, C, D. They're just switching partners. There is nothing else it could be besides double replacement, because double replacement is the only one besides combustion. So if you don't see CHO and you have 2 compounds on the product side, you know it's a double replacement reaction. Okay, and what do I mean by compounds? I mean they're 2 or more elements, right? Only double replacement was set up that way. So there's the stem of that, and now I just need to balance. All right, so let me see. I have 2 silvers on each side. I have one NO3 because we can treat them like a unit on each side. That's balanced. I'm going to move on to my hydrogens. I have 2 hydrogens on each side. And I have, oh, this was already balanced. That happens sometimes. So we just have coefficients of 1. All right, so for the next one, this is a combustion reaction. We talked about how to balance that before, but I just want to show you the stem of that really quick. If you ever see the word, some hydrocarbons, some combination of C's and H's, maybe you know at the end, usually not, and you see the word burns, okay, this should be a quick indication to you that we're dealing with combustion, okay? Something burns, combustion, okay? Something when it's in a combination of C's and H's, O's. Okay, so you would write that out like this. Always the second one, O2. And then we're going to have CO2 plus H2O. You can balance it from there, just like how I showed you on the one before. So our next one, again, we're thinking double replacement for 13 because I know that this is a compound and it's being added to another compound. So that's my only options. When I have 2 compounds and end up with 2 compounds on the other side, has to be double replacement, not single replacement. So let's practice writing out that formula. Sulfurous acid. So that you have to remember your acid naming rules. The OUS, remember we said like dynamite, ITE is dangerous, OUS. So sulfurous acid was originally sulfites. So acids always begin with H. Always, always, always. And then we're going to remember that sulfites on your polyatomic ion list. Sulfite is SO3 with a -2. So that -2 is going to go with the hydrogen, since hydrogen has a 1. And I'm going to add that to potassium nitride, IDE, so I know that was just originally nitrogen, K, and nitrogen has an oxidation number of +3, so when they crisscross, that will go over there. see how there's nothing else this could be but a double replacement reaction because these are both compounds. So before you panic and decide you can't do it, just take the time to write out what the symbols are, right? Change them from a word to a symbol, and it will probably become pretty evident what's happening. Now from there, we can write out our products. Again, just take what's acting as the cation or as the metal. Hydrogen can act like a metal in this case. And you're going to pair it up with the other one that's acting like the non-metal. Okay, so the hydrogen is now going to be paired up with the nitrogen to make our nitric acid. And the potassium is now going to be paired up with the sulfide. Alright, so again, that has a -2, so that's going to be right there. Sulfide has the -2 charge, that's where that came from. Now, one thing you want to keep in mind with a double replacement reaction are your solubility rules, because not every single reaction will work. So, secret for everyone who is watching this, we are actually going to give you this on your exam tomorrow, so hopefully that will be a bit of a relief. So hopefully everyone's going to watch it. So we have got SO3, and you want to be just making sure that everything, you're going to have at least one thing that's going to be insoluble. We've got that's going to be, we're looking on our list, and I don't see that as some exception, so I think this in fact is going to be insoluble because of the sulfur, so we're going to have, that will work. Alright, let's see, I'm going to try and see if we have an example of one. You need at least one of the products to be on your list, but we're going to give you this list so it should be pretty easy to follow along with. Okay. So, next problem. I'm going to do this one because I want to show you how this would look. Number 15. So, potassium is added to water. Okay. Now, instead of writing it out as H2O, I recommend when you see water in a single replacement situation to write it out as HOH. This is something that's going to be very helpful because it makes it easy to see that this is a single replacement reaction. Okay? I know it's single replacement because I have one compound and one thing that is all alone. So when that happens, you're dealing with a single replacement reaction. That's the only thing it could be. The K is going to go in and try and replace the hydrogen. And I want to be sure that this will even occur. So I'm going to check my reactivity. And potassium is at the very top. So it's definitely going to be able to replace the hydrogen. Okay, so that hydrogen is going to be left alone. It's going to be kicked out. Remember, Brinkelhoff. If it's in a Brinkelhoff, so if it's Br, if it's bromine, iodine, nitrogen, hydrogen, oxygen, or fluorine, it is diatomic. There will always be a 2 down there. So we've got the hydrogen all by itself because it got kicked out, and the potassium is going to be with the hydroxide. And then we just need to balance. Alright. So, on the left side, I have one potassium. I can look quickly and find my problem, and that's going to be the hydrogen. So I am going to put a 2 on the other side. When I do that, though, it also creates a place where I need to balance out my hydroxides because the coefficients distribute to everything. So I have 2 hydroxides on the left, and now I need to put a coefficient of 2 on the other side so I can make sure that my hydroxides are balanced out. Remember, the reason we write it out this way is so it's easy for you to see what's going on, that it's a single replacement, and it also makes it easy to balance because we can treat our polyatomic ions as a single unit. So I have 2 potassiums now along with my 2 hydroxides, which means I need to go back and put a 2 right there. Then we're all balanced. And I just realized we didn't go back and balance this one. Let me make sure this is all balanced. So we have K2. Nope, it's not. I'm going to go back and balance that. So don't panic if you see a situation with 3s and 2s. They have something that you can multiply them by to make them equal. Okay, we're just going to try and make them 6 on each side. I have 3 potassiums on the left. I can make it equal to the other side by just putting a 2 right there. Okay, once I do that, I have 6 potassium, and I want to get 6 on the other side too. So I'm going to put a coefficient of 3. Again, I have 6 potassium. On this side, I now need this one to be balanced out. So I'm going to continue. I have 3 SO3s over here, and I also need there to be 3 over here on this side. Alright, so this changed my last hydrogen. Now I have 6 of those, so I'm going to have to change, I'm going to have to change a couple things. Alright, so I have 6 here. I need to make this one 6 as well. I'm going to put a 2 there. But now this changed my nitrogens again, so I'm going to go back. And that happens. It's not a situation where you need to panic. Sometimes you just pick a place that's a little bit, it's kind of luck of the draw, right? Don't panic. Just means you need to go back and balance everything out again. That's okay. So I have 6 hydrogens now. I have 2 nitrogens. Oh, I didn't. Oh, actually, that balanced everything. Yeah, I'm good. So if you have to go back and make corrections, that's okay. Just cross through it. But I think we're all balanced out. So we have 6 hydrogens on the left. We have 6 hydrogens on the other side. We've got 3 SO3s. We have 3 SO3s on the top side. We have 6 potassium over here, 6 over there. We are balanced. It's balanced. All right. So let's do maybe another double replacement. Strontium hydroxide is neutralized with acetic acid. So don't panic. Don't worry about all this. Just start by changing your symbols or changing your names into symbols. Okay, strontium Sr, hydroxide is a polyatomic ion OH. Strontium has a charge of +2, so that's going to go over to the hydroxide. Hydroxide has a -1 charge. You don't have to write the ones. Okay, first part. And then just start again by writing the symbols. Acetic acid, okay, because it's an acid, I know that H is going to be in the first part, and the acetic part is just going to be your acetate. Okay, so that's C2H3O2. Alright, so here we go. And I know this is a double replacement. I wrote too big, but we'll just write this one a little smaller. So what's going to happen, the strontium is now going to be paired up with the acetate. And the hydrogen is going to pair up with the hydroxide, which of course would make water, but we're going to leave it as HOH because it's easier to balance. Okay, so that's a double replacement reaction, and so if you can just take it one step at a time, don't panic, one step at a time, it will be okay. Now we can go back and balance. I'll probably get onto our question sums here and show you the balancing at the end. All right, magnesium is added to a solution of potassium nitride. So magnesium, don't panic, just write your symbols, is added to potassium, K, nitride. Nitride, IDE, you should be thinking this is on the periodic table because it ends in IDE and not in ITE or ATE. So it's not nitrate, it's not nitrite, it's nitride. So that just means it's an N. And it has a charge of +3, so of course they crisscross. The 1 from the potassium will be going here. We don't write that, but we will write the 3 down. All right, so once you write it out, it should be clear that this is a single replacement reaction. Now, we want to double check before we continue on with a single replacement reaction. Use your activity series. Make sure this would even happen, okay? So potassium is way up top. Potassium's up there. Guess what? Magnesium is below that. That is not a good trade. That potassium is not going to be replaced. So this would be no reaction. That is not going to happen. All right. So, continuing on. Which one do we want to do here? I'll do this one as a decomposition for 16. Oh, I should balance this, yeah? No, I don't need to balance it because it didn't happen. All right, beryllium oxide decomposes. So that should give you a hint. This is a decomposition, right? So beryllium oxide. Now we can think about our charges. Beryllium is in the +2 and oxygen's in the -2. So because they're the same, I'm just going to write it like this. It will decompose. Beryllium plus O2. So we do want to be careful again for our Brinkelhoff. The reason it's O2 is because it is a diatomic element and it will not exist freely. Always has to be paired up. If you don't remember that, your whole reaction will be off because, of course, if you didn't remember that, then you wouldn't have your proper coefficients at the end because that 2 there means we have to go back and put coefficients because we need 2 on both sides. And that would change that beryllium. All right. As our practicing here, we've got our iron 3 reacting with sulfur. Okay, so originally it's just iron. Remember, before it bonds, it's just in its regular state. We don't assume that it has a charge. So I'm going to go ahead and let you finish that last problem on your own. And then whenever you're ready, turn your page over to the final page of the review. And we're just going to do a few of these because this video is so long already. Okay, so we're going to look at this diagram to answer the question, does this reaction abide by the law of conservation of mass? Count the dots. So I have 2, 4, 6, 8, 10, 12 white dots. 3, 4. Yep, looking good to me. All the dots are equal. If you count the white dots and you count the black dots, they're equal on the left and right. So yes, literally all I had to do was count them up and make sure they matched. So the reactants, okay, what happens before would be described. These look like mixture. So it's 2 different things. So we've got 2 different elements in there. But at the end, once they are a product, now they're compounds. Okay? Because they bonded together. What type of reaction is taking place? This looks like a synthesis reaction. synthesis. Okay. So at the beginning we had two different types of elements, so a mix of two different elements, and they came together to form a compound. All right. What is the mass of the solution in the second flask? Okay, so you know it's a law of conservation of mass. Products equal reactants. So this side is also equal to 225, but we only know about 100 so far. So really all you have to do to get the answer is to subtract. Okay? So 225 minus 100, which is of course 125. All right. This is the same type of question, so I'm going to go ahead and let you answer that. But remember, products equal your reactants. That's the law of conservation of mass. So if you can figure out how much you have on one side, you can figure out how much you have on the other. What type of reaction is this? This is a combustion reaction. Combustion. Okay? So that's going to do it. I know this was a lot. And study hard. Great job.